at the same time just now, a boring committee and my kid. So if I want to end a little bit earlier, forgive me because I'm just not in the mood. All right, so nobody did the bonus. One last. Okay, well, I have the solution ready. I will just give you a peek. It looks like this, okay? At first, you may look weird. You got a tangent, a hyperbolic tangent here, but it's really just e to the x and e to the negative x. So go online, check Wolfram, and see how people did it. Either way, we got this solution, okay? But the interesting part, of course, is try to solve it using a computer and try to see what's going on. So it is separable. We solved this logistic last time. This is just an example to show you what logistic looks like and also to show you how to code a slider in Python because it can be quite neat. Say if you got a maximum capacity as 1,000, let's say, oh, 1,000 is my maximum. Okay, 700. And you have a parameter, which is the growth rate. Once you have a slider, you can easily manipulate those things and try to see how your graph is going to change according to this. So what I did is you start with 200 population. You have a growth rate of 0.5 and your maximum capacity is 700. Then what you did is you basically have a logistic growth and eventually that thing hit the horizontal asymptote because you could never pass the capacity. That's what you got. Now what you can do is you can change the growth rate to be slower. You can see you still have the same capacity. You just reach it with longer time. Of course, as you increase your exponential growth rate, you can achieve this one faster. Similarly, if you have a fixed rate, and then you start to increase your capacity, what will happen is the steepness of your curve doesn't change much, but your maximum capacity start to shrink or increase. So this is really a quick way for you to solve any differential equations using a computer and then try to adjust the parameters inside to try to see what does each parameters do to your final solution. And eventually through there, you get some inferences about what the parameters does. Okay. Now we're going to go and solve this one. This is going to be the one free diving one. How many parameters do we have? We have M and G, they're fixed. We have a K, which is basically how big the area resistance is going to be. And let's see what's going to happen here. Okay. So number one, with a fixed M mass and a fixed rate K 0.5, you can see eventually your velocity is going to be really, really fast. And eventually, up to a certain point, you receive a horizontal asymptote. Okay. That means if you do skydiving at first, you may be just dropping really, really quick. But after a while, at a certain height, hopefully before the ground, you hit the constant speed. Okay? Then that is actually your safe speed. It will be like that all the time because simply your area resistance balanced your gravity. Okay, from now on, you will do a constant speed dropping. Sounds good? Cool. Now let's just increase the area resistance. What do you think will happen to your curve if I just increase K? Well, then your final velocity should be slower, right? Okay, and does that make sense here? Because you increase fewer time, simply because you achieve the balance earlier, simply because you have a bigger area resistance. So you should expect to see this curve to drop down. Okay. Now I'll fix the K. What if you go there and do a skydiving and they find a guy who is twice your size, do the same skydiving? Is there a guarantee that your parachute is safe? We'll make sure that his parachute is safe. Well, remember the area resistance is only related to K and your velocity. It has nothing to do with your mass, so it's fixed. But your gravity does. Okay, so if you increase the mass of the person who is on the parachute, what's going to happen? Can you see that your end equilibrium velocity is going to be faster if you have a heavier person? Sounds good? Okay. So now with this differential equation you just solved, you can add more parameters in. Now it's a really interesting thing about putting a parachute in. Okay, assume you do skydiving with nothing. This is how you're going to dive with air resistance. Okay. Now if you start to take a parachute, what's going to happen is the parachute is going to change the K because it basically changes the area. You receive the air resistance, which is from pressure. The bigger the area, the bigger the air resistance. So basically what you're trying to do is you're trying to manipulate K by putting a parachute there. And your final goal is try to make sure that, because eventually this will be the speed you hit the ground. You're trying to manipulate it such that this one is below a certain threshold, so it's safer for you to land. Make sense so far? Okay, so that's almost like the easiest example I can show about a control problem, and also about how do you use simulations to design your study, and then finally to direct your manufacturing. How do you make a parachute? You better test it, you better test the K, and make sure that the K is safe. And you do that by manipulating Ks to get the desired speed. As we showed just now for the same K, different M matters. So when you give instructions for those kind of parachute, you better tell people how heavy you have to be in order to use this size of parachute. Otherwise, you're not safe because your speed will maybe higher. Okay, that's another example for skydiving. Again, this one is separable because you can move everything with respect to V on the other side, T this side, and then start to doing integrations. Now let's go over another one, which is the Friedmann's equation. We cannot solve it, but nonetheless, it's a separable equation, so that's good. The problem is it's nonlinear. Example 1, skydiving. Example 2, Friedmann's equation. Okay. This one is used to study the expansion of the universe. All right. I think everybody knows that our universe is expanding. This can be verified by experiment. So it is expanding. Now think about the distance here, d, between two things. Usually what we do is we put a coordinate. We say you are at 0 and I am at 2 or 3. That means I am 3 units away from 0. Okay. Now when you say something is expanding, there are two ways of representing it. The first way to represent is actually originally you're from 0 to 3, now you're from 0 to 4 for the same distance. Your coordinate change. That's one way of calculating it. Okay. There's another way to calculate it. That is, once you expand, going from here to here, you are still from 0 to 3. So your coordinate does not change. Okay, but instead, the unit changed. Or let's say the reference of the frame keep expanding. That's another way to quantify it. You fix one, you let the other one change. You either fix the reference frame, you change the coordinates, or you fix the coordinates and you change the reference frame. Either way, it's going to work. We are going to go with this way because it's easier to compute. All right. So let's take some distance. That's x. Okay. by coordinate. Now the real distance, we name it x times d, where d is actually the length of the unit. Okay. Oh, real distance is d. Okay. Then what we can do is we can say d is this times at, and this at is going to be the length of unit, and it's increasing. Basically means before this is 1, after a while this is 1. Okay. And this one change according to time. While x is the constant. Good so far? Now let's talk about the velocity, v, which is nothing but d prime, or more precisely, dd dt, which is dxat dt, which is x is a constant, a prime. Okay. So now finding how fast our universe expands is equal to find at. And what we're trying to do now is we're trying to set up a differential equation for at. Still okay so far? Now let's do some very transformations. Let's keep this thing. Let's keep this thing. We divide by at, we times by at, which give us nothing. But then we put these two terms together. We realize this is d times a prime t over at. We give this thing a name, h. Does anybody know the name of this constant here? Hannah?
Hubble's constant.
That's Hubble's constant. So what we really saying is your velocity is going to be d times a constant. The h is Hubble's constant. That means the further you are, the faster you move away. Hannah, question. Why is this one called Hubble's constant? Clearly it's not a constant.
Because Edwin Hubble discovered it, I think.
That's the reason why it's called Hubble. But why is it called a constant? Because clearly this one is changing with respect to t.
They used to think that the expansion was constant, but they discovered in the 90s that it was accelerating.
Makes sense to everybody? So that is actually before we know the whole thing is expanding. So Hubble's constant, they think is a constant, but really it's a constant with respect to x. Or let's say space. That means this constant is everywhere the same. It's the same on the Mars. It's the same like 5 million light years away. But actually this one is changing with respect to time. Does anybody know how to measure it? Anna?
You measure the distance through a variety of ways to distant stars and then find their velocity, and then you
Great. So
can
we
put them
measure
on
the
a graph, and
distance.
the slope of that line is.
We measure the distance. We measure the speed. How do we measure the distance though?
There's a lot of ways you can use parallax or Cepheid stars or.
That's one way, clearly. Okay, so we do have one way you just suggested. This is doable because we know how far the stars are away from us by measuring, for example, the strength of their light. Or like Hannah said, you assume the galaxies, they have a constant distance between each other. So you can see actually as they move far, far away, they're closer and closer to each other. So you can use that thing. How do we measure the speed? How fast that thing is moving away from us? How do we measure that? Hannah, you should know this, right? This is your research.
I can't remember off the top of my head.
Okay. Yeah, think about it. You got a galaxy, right? Sending your waves. That's light. You know, different light have different colors depending on their frequency. Oh, Doc, go ahead.
I was going to wager a guess that it had something to do with the integral of a prime t, but I'm guessing that's not, because you just started talking about diffraction, so I didn't want to interrupt on that.
That's the problem, though. If you have AT, you can find A prime t if you know the function. But now all you got is just data. You know AT at t equals 10, for example. Okay? Now, in order to measure, so you're suggesting if you know AT, you should know A prime t. That's good if you have something like that. That's your AT. Then you just use your AT minus, is that technically AT plus 1? Minus AT divided by basically how long it takes you for this gap. You got the derivative approximately, right? The problem here is that like this one is changing really slow. So you probably have to wait for 100 years for this to happen, or maybe 500 years. So that's not going to work until maybe 2,000 years later. We just wait. Okay. Anybody knows? Doug? You still? Oh, sorry. Colin.
Do you use redshifted light?
Can we describe what is a redshift?
So as an object moves away, it emits a constant wavelength of light, but as it moves away, that wavelength is stretched out.
Okay, so it's the Doppler effect, right?
Yeah.
Okay, what we got here is we got something moving away from us. Let's say this is the observer. This is us. I'm going to draw myself. Taking a telescope and watching this thing go moving away. So now if this thing doesn't move, I'm going to receive a light. And I know what color that light is because I know the frequency. But now as this one moves forward, what you are going to get is the whole thing got stretched. So I'm going to still receive the light, but the light is stretched. That means the frequency is lower than it should be originally. And that is called a redshift. Because red light is said to have longer wavelengths, therefore lower frequency. Okay, redshift basically means your frequency become lower, and you can determine how much lower, and in this way you can tell how fast this one is moving. Okay, so that's a simple relativity thing. It's basically telling somebody is moving away from me simply because the wave they sent me is got stretched. Awesome. So that's the law. This is the constant, but actually it's a constant with respect to t. We just didn't notice at the beginning. All right. Now how are we supposed to set up an equation to tell us how fast the universe is expanding, or let's say how to find AT? Well, we use Newton's law, particularly conservation of energy. Let's just say we have a lot of galaxies or whatever, right? Things like that. Roughly like a sphere. Now what we need to do is we just focus on this one little object here. let's talk about two things. The first thing is going to be the kinetic energy. That is going to be 1/2 mv squared. The m is actually the mass of this small object here. Later we will see it doesn't matter. The second thing is going to be the potential energy. That's Gmm divided by R. Okay. And it's negative potential energy, so we should put a negative here. Now by conservation of energy, the first energy plus the second energy should be a constant. We just name it a constant K. All right. That's the equation. Now let's try to put A in. Remember, D is ATX, and your V is HD, which is XAT prime. That's the two things you know. Therefore, automatically you can have this. That's 1/2 mv. Okay. Minus G, that's a constant. M, your R is nothing but the distance from here to here. That's your D, that's XA. Equals K. Now you divide this M on both sides. That becomes K over M, which is another constant. Let's still call it K. Okay. Finally, you have your capital M. You are talking about the mass inside a sphere. So the mass should equals the density times the velocity, not the volume, which is nothing but rho times 4/3 pi r cubed. And again, your R is going to be your XA because that's just your D. Putting everything together, 1/2 V square, which is XA prime square, minus GM divided by R equals K over M. Let's just call it K. Okay. Let's simplify a little bit. That's going to be X square A prime square. This times the 2 minus G rho 8/3 pi X square A square equals 2K, which we just again denote by K because it's just a constant. Divided by X squared because it's not important. Again, that's just a constant. So finally, if you clean out everything, the final thing looks like this. Minus K over A squared. You probably need to times the C squared because I treated the velocity of the light to be 1. But if you change the unit, you just times the velocity of the light there. This is called the Friedmann's equation. That comes from the conservation of energy and these two simple facts. D equals AX and V equals XA prime. Sounds good? All right. A square, C square. KC square. Yes, okay. Yeah. Should be actually just, let's just use K. Doesn't really matter. Oh, sorry, K over A square. Everything makes sense so far? Now the beauty is, how do we solve it? Think about it. If we solved it, we will know AT. If we know AT, we know how fast the universe is expanding. Okay. So first assumption, K is super small. That's the first assumption I make. Not assumption, that's observation actually. Yeah. So basically we're solving A prime over A square equals 8 pi G3 rho over rho, roughly. This term, we just throw it away because it's so small. On the left, you have A prime and A. On the right, you have a constant. Is rho a constant? The density? Think about it. You got all these matters. Okay. And your space is expanding. There's no way your density is a constant. Your density should be reducing, right? It should be decreasing. Still okay? So what we need to find is just the formula for rho. And it's actually not hard to find. It's just some constant, which is your mass, divided by A cube. Because you're talking about volume. The volume is expanding. Make sense so far? We don't know what capital M is. We don't care. It's just a constant. Then what we have is nothing but A prime over A square equals a constant times a constant together, a constant divided by A cube. Or more precisely, A prime square equals A prime square equals C times, there's another A square here, so times 1 over A. Make sense so far? Okay. Question, is this one separable? It is, right? All the A on one side, it's separable. Beautiful. Go ahead and try to do the integral. Okay. You know A prime dt give you dA. And now you can see you have trouble because one of the A prime go. The other A prime stay. There's no way you can do the integral. Make sense so far? So this is separable, but not linear. Therefore, everything we did before cannot work. It only works for first order linear separable equations. We need something else. Okay. So how do we solve this? Can you make a guess? Doesn't look like sine, cosine, does it? Exponential, and then you have exponential square. That doesn't look like a constant, not really. Okay. Polynomial, maybe t to the, I don't know, t to the square times t prime square, which is 2t square. That give you 4t to the fourth. Make sense so far? For this one become interesting because every time you have a polynomial, its derivative is also a polynomial. And polynomial times polynomial, does it ever equal to a constant? Think about it. If you play it right, you may have a zero order polynomial. You just need those kind of things to be really, really tricky. It has to be very special numbers. Make sense so far? If that's the case, I'm going to make a guess. The solution is roughly t to the k. It's a power. I don't know which power, but it's a power. So if a is roughly t to the k, remember there may be some constant, we really don't care. A prime is roughly k, t k minus 1. But really, we don't care about k. It's just k minus 1. You want a prime square times a is a constant. Oh. You just need a square is t 2k minus 2. A is tk. A this times a is nothing but t 2k minus 2 times tk, which is t 3k minus 2. You want this thing to be like a constant. You just need 3k minus 2 equals 0, which give you k equals 2/3. So it's settled. A is roughly t to the 2/3. With some constant, I really don't care. It's roughly a polynomial. It's slower than linear. Okay, the details are easy to follow. I think everybody can follow it. You can also check the lecture later. But think about how we got it. We start with a Friedmann's equation, which is a conservation of energy. Then we ignored this term because k is in general very small. Then what we got is we give a formula of rho, which is very easy to do because rho is inversely proportional to the volume. And the volume is nothing but a cube times a constant. Okay. With these two assumptions, we guess the solution. And finally, we have this interesting final result. A is roughly t to the 2/3. Sounds good? That's case 1. Now you know what we're going to do for case 2. We pick another rho. We solve it again. Okay. Before we set the rho is this. Okay. Why? Because your density is proportional, inversely proportional to your volume with a fixed matter. Okay. That makes sense, right? But there's a problem. That only makes sense if all the energy within is actually in terms of matter. What if the temperature is really high? I'm talking about extremely high, so no matter can actually sustain. And they all become radioactive energy. Then we need to change the formula a little bit. Okay, it's still the same. Here you should put the energy or the matter, which is the same thing. Before we assume as we expand, of course, the matters are pretty stable, so your matters stay constant. But now if you think about it, when things are really hot, your photons, actually not photons, let's just talk about radioactive wave, right? And here's the interesting thing. The number of photons, of particles or waves, is inversely proportional to the volume. The bigger the volume with the same number of wave, it's still 1 over a cube. But now for each individual wave or each individual radioactive particle, your energy also reduce. Because if you keep the velocity to be the same, you let the space become longer, your frequency become lower. Make sense so far? So each individual one, energy is also 1 over a, because the bigger the distance, the bigger the space, the lower the frequency, the longer the wavelength. Together, this time your rho should go to 1 over a on the top. It's decreasing if you keep the volume to be the same, and actually not the same, expanding. Similarly, the bottom is going to be, because the number of waves are also decreasing. Together, it's 1 over a to the 4th. I will skip it. You put that thing in. It's a constant, this time times a to the 4th. You solve it again. You got a prime square times a square equals a c. A still is a tk. A prime is still tk minus 1. The a prime square is going to give you t2k minus 2. A square gives you t2k. You want 2k minus 2 times t2k equals the constant. Your 2k minus 2 plus 2k has to be 0. This implies k equals 1/2. Therefore, a is t to the 1/2 for this case. Sounds good? Okay, let's summarize the table. We have two cases. The first one is early universe. Everything is hot. Therefore, radioactive. Radiation dominant. Therefore, your rho should be proportional to 1 over a to the 4th. Your a is proportional to t 1/2. Second case, things cool down. Cool down. Now instead of radioactive, you have matter dominant. Everything's stable now. Then your rho this time is going to be 1 over a to the cube. Then your a is roughly t to the 2/3. Time a. Remember, a quantifies how fast your universe is expanding. Can you draw it now? At early, you should draw this. That's roughly a square root. Big Bang. Then your universe expands at a certain rate. After a while, you cool down. Instead of this one, you should take this one. Is that one faster or slower? 2/3 and the 1/2. 2/3 is bigger. Therefore, this one's faster. Not as dramatic as that, but this one's faster. But this part should be smooth because you're kind of radioactive and matter dominant at the same time. So this is T to the 1/2. This is T to the 3/2. Sounds good? Do you wonder what's after this? We have a third case. What's the third case? Well, technically, the whole thing is let me say we don't need this because K is small. Sounds good? Okay. But now look. K is like that. What about your rho? Your rho is either 1 over A cube or 1 over A fourth. And this one is 1 over A square. Still okay? So no matter how small K is a constant, right? When A is extremely big, can you see this one become a dominant? The first term started doesn't matter anymore when A is huge. Make sense so far? Okay, so when A is huge, actually it's the reverse. This term become negligible, but this term become dominant. And it's very easy to solve. That's A prime square equals, did I have a plus or minus? I should have a plus here. Did I do plus or minus there? Whoa. That's a plus here. Okay. That's a plus here. So that was okay. Messed up this sign. Okay. That means A prime over A square roughly equals K over A square. That means A prime square is roughly K. That means A prime, whatever, is roughly a constant. Okay, as A become big, this become not important, no matter how small K is. Then the second term become the dominant one. This one has an A square, this one has an A square, they cancel each other. Therefore, the prime is nothing but K. Then A prime is nothing but just a constant. Good so far? Do you know how to solve this? Something is wrong. I copied the wrong thing. Eventually rho goes to 0, K become dominant. I should have exponential. Why do I have a constant here? I should have A here somehow. Oh, yes. Take it back. That's A prime over A equals to a constant. That's A prime equals to a constant times A. That's where A is roughly e to the square root of k times t. Either way, it's just e to the t with some constant. Okay. Exponential growth. That means somehow in the original equation, I shouldn't have this square here, but I did have the square here. Let me search the Friedman equation. K c squared a squared, that thing does have a c squared here. What did I miss? Okay, somehow I mess up with my notes. I do know two things firm. Number one, I just Googled. This equation is correct. So there's nothing wrong with that. Number two, the final conclusion, this one should be exponential. This is correct. But then I missed the calculation in the middle somehow. There's a detail I didn't figure out. I thought I did. That is roughly here. The key is, does this a squared, is the a squared there? And after that, how can I solve this one still get exponential? You see where the glitch is? Okay. I will try to go back and figure it out. I thought I did, but then I made a mistake in my notes. I just took it for granted. Okay, I thought it's easy. Sounds good? Cool. So for the third case, now we can complete this thing. 1/2 at first. Radiation dominating. 2/3 second when you have matter. Eventually, at some point, K become dominant. Then the whole thing start to become exponential. Sounds good? Okay, that's the whole thing after we solve the Friedman's equation. We got this three phases of the expanding of the universe. First slow, then fast, and eventually scary because it's exponential. Okay. Where are we right now? We are right here. So we are very close to where K becomes dominant. We're actually very close to when everything grows exponentially. Okay. Does anybody know the name for this K here? It's so small, originally people think it's 0. Okay. That is actually where the dark energy comes from. Or what's in the Einstein's general relativity equation, the cosmological constant. Okay. It's related. It's not exactly the constant. The constant you need to divide by some ratio. Okay. But this one is clearly related to dark energy because everything is sending each other away. The only glitch here is somehow I jumped from here to here. So I should cross this out. The original thing does have this. This is where the glitch is. My suspect is I should have made it dimensionless first. Otherwise, the unit is somehow playing something there. Dimensionless first. Okay, I think that's where the mistake is. All right. Sounds good. So this is happening in our universe. This is Earth. Everything away from us is actually getting away from us because the whole thing is expanding. What's the principle? The principle is the further they are, the faster they're moving away. Okay? The ratio is quantified by this Hubble's constant. And as far as you can see, this one is going to be increasing all the time. Still, okay? There is no upper limitation of how big this one is going to be. This one goes to infinity. That means eventually this one will be faster than the speed of light. That means we're here and something is moving away from us. Then the light we receive will receive a redshift, as we said before, right? But if they are moving away from us with a speed faster than light, then there is no way we can receive anything from them. So there is a maximum distance we have right now. Right here, the distance is big enough after times h. It's exactly the speed of the light. And we couldn't receive any signal outside this boundary. Only the thing inside. That is called the horizon. And that's it. That's the furthest we can go. That's the furthest that we can observe, we can know. Cool. That's a whole set. I try to condense everything with the details into one small lecture. Seems like I made a small mistake. But other than that, I'm pretty confident the other part are correct. Okay? Any question regarding this? Good. That's all for today.